Assalamu alaikum wa rahmatullahi wa barakatuhu. Alhamdulillah. Wassalatu wassalamu ala Rasulullah. Amma ba'd. So now we continue our lecture from the previous lecture. Previous lecture was part A of the lecture on the steady state error, and in this part we will be discussing the some more detail of the introduction section. So here we see the stability consideration. That first thing which is important, that the closed loop should be stable. If the closed loop is not stable, then there is no need to discuss the performance of the system. And what is the reason? The fundamental reason is that if the system is unstable, whatever the bounded input we give to the system output C of t will tends to infinity. Like suppose we had any system T of S, and to this system we give any bounded input, like suppose 5u of t. If T of S system is not stable, unstable system, in that case the output of this C of t will be equal to infinity whenever the time t tends to infinity. So whenever this happens, so definitely the input R of t is bounded, so a bounded value minus C of t, which is infinity, it will approaches to infinity, and when we say infinity, this means this is plus or minus infinity. So to discuss the steady state error, it is important that first we should assure the closed loop of the system is stable. When I am saying closed loop of the system, like we have an open loop system G of S, and now this G of S not necessarily be stable, it can be unstable. But once we design a closed loop, like we have a controller K and we have a feedback minus plus, and here is the reference input R of t and the plant output Y of t, we say that whenever this loop is stable, then we can talk about the steady state error. And when we say steady state error, we are talking about this error when the transient die out. So you should understand this, like this closed loop should be stable whenever we are talking about the steady state error. So evaluation of the steady state error, we say to this sometime SSE, steady state error. Normally we consider two type of system. The first type is the unity feedback system, and the other one is the non-unity feedback system. In this lecture we will focus on the unity feedback system, and by the way, next 4 lectures will also focus on the unity feedback system, and the 6th lecture will be discussing about the non-unity feedback systems. So the steady state error can be because of two fundamental reasons, and the first reason is the non-linearity in the system. Like there are several type of non-linearities. One of them is like backlash. There can be other thing like saturations at the input and output, some other type of non-linearities, but those topics are not related to our discussion. We will be discussing only that whatever the steady state error is coming due to the dynamics of the plant G of S. When I say G of S, I am talking about the transfer function. Of course, this model can be in state space, or this model one can write in differential equation format. But whenever this system is linear, and due to the linear dynamics of the system, how the closed loop is behaving. So the main topic of the discussion is that that the unity feedback, we are saying that whatever is the output is there, we directly bring it back and we subtract it from the reference input. Here the reference input, we are showing it in the RS, which is the Laplace transform of the R of t. R of t is the reference input, and sometime we say that this is the desired output. Similarly, this is the Laplace transform of the output of the system, and of course the original output of the system in time domain is C of t. So in time domain, this error E of t we consider is equal to R of t minus C of t. So for any control system, the input R of t is bounded. We normally give the bounded signals to the as the input to the system. So if this closed loop is stable, if this complete closed loop is stable, then definitely C of t will also be bounded. And if it is bounded, then definitely E of t is equal to R of t minus C of t is bounded. Otherwise, this signal E of t will not be bounded. And what is the reason? Like if this closed loop is not stable, like over here the closed loop, this closed loop, if this is not stable closed loop, then definitely C of t is not bounded. And if C of t is not bounded, so definitely R of t minus C of t is not bounded. Normally we say R of t is a reference input signal, but in applications this is the desired output. Like in your room, if there is a air condition and you want to control the temperature of the room, so what you do? You normally put over there say 25 degrees centigrade. Like you want to make the room temperature 25 degrees centigrade, so using the controller you adjust it to 25 degrees centigrade. So after some time your room temperature becomes 25 degrees centigrade, and this 25 is the, over there we say it is set point because it is constant. It is a set point, and we say to this set point because it is constant, but this is a reference. But in some cases, like the robot path, like suppose you have a robot and you want to move this robot from point A and you want to make a trajectory like this, and from point A you want to reach to point B, but by following a definite trajectory. So this trajectory is the desired path, and you want that your robot should go on this particular path. So then we say that this R of t is the desired signal, desired output signal. This is reference, but we say it is the desired output signal. So these are few explanatory points you should keep in mind that whenever we will be talking about the error. So here it is written E of S. E of S is fundamentally is the Laplace transform of the E of t. So E of t and its Laplace transform will be E of S. So we will be considering today two examples in this lecture. So from the previous slide, we consider over here this slide, and here suppose G of S is the open loop transfer function, and this open loop transfer function is equal to suppose K, and this means that the system has a gain K with no dynamics. And here R of S is the reference input to the system, and in time domain it will be R of t. In this example, we consider that whenever this reference input is a step input, this means that U of t is the unit step, and its Laplace transform will be 1 over S to the system. The Laplace transform of this system will be equal to Laplace transform will be equal to 1 over S is the input. So what will be happening to the error E of s, and of course we want to discuss about the steady state error ESS. So we know that the steady state error, to find the steady state error, first we should know E of s, and E of s is equal to R of s minus C of s. So if I give it an equation number 1, so we know that C of s is equal to the closed loop transfer function. C of s is fundamentally, we take this closed loop transfer function as we have calculated it several times. This will be equal to G of s upon 1 plus G of s into R of s. So this is equation number 2. Then using these two equations, it is easy for us to write down E of s is equal to R of s minus G of s upon 1 plus G of s into R of s, and if we take from here R of s common, so you will have 1 minus G of s upon 1 plus G of s, and this whole thing will give us with little calculations like 1 plus 1 divided by 1 plus G of s into R of s. So this is the error of the closed loop system. Now if this given closed loop is a stable closed loop, then definitely this error E of s will be bounded for the bounded input R of s. Now further discussion will give us some conclusion that E of s we are saying is equal to, for this closed loop, is 1 over 1 plus G of s into R of s, and as we said that the input to the system is u of t and its Laplace transform is 1 over s, and this value is k. So definitely we can say that E of s is equal to 1 divided by 1 plus k into 1 over s. Now the steady state error, by definition we know that ESS is equal to limit t tends to infinity E of t, which is equal to E of infinity. And you have studied the final value theorem. What is final value theorem? Anyone, if you remember, just write it. Final value theorem. What it says? The final value theorem says that if a system is stable, and over here when we say system, we are talking about this closed loop. Suppose this closed loop is stable, or the transfer function, this transfer function, this whole thing is a stable thing, then we say that E infinity is equal to limit s tends to 0 s E of s. So this is very easy for us now to write down that ESS is equal to E infinity. This means the steady state value of the error is equal to limit s tends to 0 s E of s, and we have discussed this in detail that it will be equal to limit s tends to 0. I write the s by itself, and this E of s we just calculated, it is equal to 1 over 1 plus k into 1 over s. So s will cancel with s, and we will get 1 over 1 plus k is the ESS. So the steady state error of the system will be somehow 1 divided by 1 plus k. So this means if we increase the value of k, the error will be decreasing. Like suppose k is equal to 1. So putting in this equation the value of k, we will get that ESS is equal to 0.5. Again, if this k is suppose 9, and whenever this is 9, so this whole thing will become 1 over 10. So when it is 1 over 10, so ESS in that case will be equal to 0.1. And now you check if k is equal to suppose 999. So we will be getting E of s is equal to 0.001. So increasing the gain, the steady state error will be decreasing. But one thing you should keep in your mind. In chapter 2, in chapter 4 and in chapter 5, we studied that whenever the gain of the closed loop is higher, it is possible that the system poles moves towards the zero or on the imaginary axis, and in some cases they can go to the right half S plane. So the system can either become unstable or system can become oscillatory, though the output will be bounded, but there will be oscillations. So this means that there is a trade-off between the decreasing of the steady state error and the decreasing the steady state error and the stability of the system. So whenever a control engineer designs the closed loop, he has to put attention toward these two important trade-offs. Like one side, the system should be more and more stable, and on the other hand, we want that the steady state error should reaches to zero as quickly as possible. So these two things sometimes offer the challenge, and it is a control problem. In many cases it can be solved easily, but in other cases it can create lot of problems in giving the solution to the problem. So here we give the summary, like the plant is somehow g of s is k, then we consider that the Laplace transform of the signal E of s will be, this will be the error as we discussed already, and then we can easily write g of s is equal to this. The simplification will give us this transfer function, and if r of s is the unit step, so for the unit step the Laplace transform of r of s will be 1 over s, so we get E of s is equal to this, and then using the final value theorem we reach to this result as we discussed by hand calculation. So here we say that suppose if I want to make a small table over here, like I make E of SS and here I write K. So suppose K is equal to 1 and E of S is equal to 1 over 1 plus K. So here you will get 0.5. If you put over here 9, so here will be 0.1. If you put 99, you will get 0.01, and if you put 999, here it will be 0.001. The meaning is that as we are increasing K, the steady state error is decreasing, but it will never reach exactly to 0 until and unless K is infinity, and which is not possible, and K is the gain of the system. The rest of the things related to the gain I just discussed a few minutes ago. So once again we consider the same loop what we discussed in the previous sheet, previous part. So here g of s is this, but now we consider that g of s is equal to k upon s. This means there is an integrator in the loop, and the same thing like the input to the system is u of t, which is 1 over s. And as we studied previously, it is possible for us to write down that this error of the system is 1 over 1 plus g of s into r of s. So if we insert the values, so r of s over here, this will be 1 plus k upon s into, here we will get the input to the system, like the value of r of s is equal to 1 over s, and this value is coming for the g of s. So then definitely a little bit manipulation, algebraic calculation will easily give us 1 over s plus k. So this is the error of the system if the system is stable. And whenever the system is stable, definitely from here we can know that if k is greater than 0, so the closed loop will be stable over here. And in this case, this means whenever the input to the system is 1 over s, this means the step input is input to the system. So again we can use the final value theorem to find out the steady state error whenever k is greater than 0. So in that case we can easily write like ESS, which is equal to E infinity is equal to S E of S limit S tends to 0, and this will be equal to limit S tends to 0, and for E of S just we calculated it is equal to this S, we can directly write S, and E of S we just calculated S upon K, so this limit will be equal to 0. So here we see that if input to the system is u of t and the open loop transfer function has an integrator, then the steady state error will always reaches to 0. So if you design a closed loop system and there is a integrator inside the closed loop, then the steady state error for the step input will be 0. And there are lot of applications we need this type of thing. So to such controller we say integral controller. Whatever in the previous sheet we were discussing, that is originally the proportional controller. So the summary of this discussion is somehow is like this. Case 2 we consider this as I discussed. So now the closed loop transfer function as I calculated by hand, you can get this and this will be the result. So now if R of S is equal to 1 over S, so putting 1 over S, we will get E of S is this. Then using the final value theorem, it is always easy to see the error will tends to 0. So here we conclude that if there is a integrator open loop transfer function of the closed loop, then in those cases, if the closed loop is stable, if this complete closed loop is stable and G of S contains at least one integrator, then for the unit step input the steady state error will be 0. So keep this in your mind that whenever you are designing a controller for the system and there is a requirement that the steady state error for the step input should be 0, then there must be one integrator in the closed loop, but at the same time the closed loop should be stable. So the design of such closed loops later on we will be discussing.